Okay, so here we are at the bench. We have one of the attenuator modules in question, and we're going to set up a bench test so we can more accurately, or at least more precisely, control the conditions of tests that we're going to be playing around with this guy, feeding in specific signals and watching the output on a scope. And we'll go from there and see if we can't try and at least reproduce the problem. And I'll show you the test setup for that. And I'll also pull this apart and we'll take a look at the insides of this guy as we're going along. So there's obviously any good bench should have some test equipment. So we're going to set up a test rig here with a breadboard and some basic circuitry. And I just wanted to do a quick twitch show and tell of that. And actually there's another serial number under here we can take a look at. But anyway, that's the attenuator module serial number with the option information there. So it's digitally controlled. Here's the control connector. It's an 8-pin connector, I think. Yeah. And not all wires, of course, are used. There's a gray wire and a green and a yellow that are cut. All the rest are actually plugged through here. And so this will be, we'll use our breadboard setup here to provide signals to the attenuator to be able to bring the pads, the attenuation pads, in and out. The second part of this test, or I should say the setup, will involve the use of both a function generator, which can go up to 50 megahertz. We'll run this test at 20 megahertz just because it shouldn't make a big difference either way, and it's a nice easy area for this signal generator to run into, but it can go up to 50. And we're going to scope the results on an oscilloscope. We'll directly patch it through. We've got a 50 ohm termination capability inside the scope. We'll use that, and we'll be able to visually see what's going on as we bring the attenuator pads in and out. Okay, so we've hooked up everything. This function gen's fired up, the oscilloscope's fired up, and then everything's attached and hooked up. So we've got the attenuator module plugged into our test harness here, test jig. We have 6 buttons. So the way this attenuator module works is it has 3 pads for a total of 70 dBm, a 10 dB pad, a 20 dB pad, and a 40 dB pad. I'm not actually sure that's where they are, but logically speaking. And each pad is activated by a solenoid, and the solenoid is a latching style, so it's got both an in and out signal. So there's a common plus 20-ish volt signal, and that gets not shunted, sorry, it gets directed through one of the solenoids, either in the enabled or disabled or in or out setting. So plugged into this, we're going to provide power here with our trusty bench supply, and I get to show this guy off. I love this one. So we're going to set this for just over 20 volts, and right now the limit is set for about 0.5, 0.7 amps. So we'll go ahead and plug that in right now. Of course, we should be taking nothing because, of course, we're not using anything. If we were to try and bring one out, there you go, you can hear that attenuator. But as we bring that in and out, you're going to see it's going to use some current. So we're going to right away. So we're going to just do a quick check now of the test and measurement setup. Okay, so what do we have here? Okay, so we've got the function generator. Now it's set for 20 megahertz. And if we look at the amplitude, we're setting 200 millivolts. And the offset at 0, so it's going to be plus minus 100 millivolts, obviously, around ground. And on the scope, we have it set for, we're going to use channel 2, and it's set for AC coupled input, 50 millivolts per division, with the 50 ohm termination enabled. We're going to measure frequency, duty cycle, which is not that important, peak to peak, and right now you can see obviously we have no signal going through because we have the output disabled. So let's go ahead and enable this output, and we should see the signal generate to, or jump out immediately to 20 volts peak to peak. And there we go. So we have our 20 megahertz signal here, and we have 1, 2, 3, 4 divisions. So that's our 20 millivolt peak to peak at 50 millivolts per division. So everything's fine and sweet there. So we're going to go ahead and right away we're going to go and try and fire in one of these attenuators. Okay, so you can hear that's out, it's in. Alright, so let's go see what's going on with everything on the scope. So, I'm just going to do this, zoom in a little bit, so we can get a better view here, and hopefully that's nice and easy visible. Okay, so out, there's our signal, looks great, fantastic. So we're going to bring in the attenuator. Okay, so now you can see it came in, it's attenuating. I'm not going to bother calculating for the moment because obviously it's working. And right now I'm at the point where I'm troubleshooting, does it work, does it not work, and why is it not working in general, not looking at the level of attenuation at the moment. So clearly this attenuator seems to work. I don't see any lag, I don't see anything weird. That one seems to work fine, so let's leave that one out and let's go to the second one here. And right away, oh, okay, so that's not so bad. Oh, but that, hang on a second, so this is with the attenuator in, so this is probably the 40 dB attenuator, and when it comes out, you can see there's a little bit of a lag going on there. It's not instantaneous. Oh, yeah, there's something wrong there. Now that means, and of course this is in, and when we see this little lag, it's when the attenuator is coming out, which means that it's when the pad is being pulled out of the RF pathway, and we'll see this a bit in a second when we take it apart. That's really weird. That means there's probably not a contact being made very well somewhere. Let's continue on with the third one. And again, this is just like the first pad. This one's coming in and out nice and clean. And again, I'm not sure about the value of the attenuation, but that looks about right. I mean, you know, we should see 3 major levels of attenuation here. So we have the first one again. Okay, that's, you know, okay, so that's not too bad. And this one's again more attenuated. So this is probably the mid or the medium value, or the medium attenuation. So it's probably the 20 dB. This is probably the 10. And this, which with the pad in, you can see we can't get any signal whatsoever. So this is probably the 40 dB attenuation, which would make the most sense. So I think the time has come to pull this sucker apart and see what we got in here. So I'm going to, having taken this apart already more than once, I kind of know where to start. So we're going to start on this side, and we'll pull this apart right now. And of course, these screws are not in very tight because I didn't want to have to muff it up on camera as I undid this. What we're going to find in here is, in fact, actually the whole thing comes apart quite nicely to see the mechanism, the actual solenoid, the plunger mechanism to turn this on or off. But to get at the actual RF pathway, it's a little more tricky. So here we go. So here's the one end we can pop off here. We have a little bit of, looks like shielding of some sort. And we can start seeing right in there. There's all the good stuff. So, nice thing about this design is that the housing just slides right off like this. Piece of cake. And there we are, we're in. So, we have a little circuit board here, which is nothing major, just to reroute some of the signals. And you can, it's sort of hard to see, but you can see the solenoids are right here. And we've got 3 of them, 1 for each pad. And it's really difficult, but we might be able to see it right there. There's, you can just barely see it. Where's my, there we go. If you look in there, there's a plunger in there. Right in there. Now, each of these attenuators, so the solenoid will actuate in and out like this, and there's 2 plungers, one on each side of the one on each side of the attenuator pad. And we'll see this when we pull apart the actual RF. The RF pathway to take a look at the actual pads themselves. We'll see how that works. So right away, we could probably actually do some tests right away, not right now, but we'll go a little deeper, and we'll see first. We'll take this apart a bit more, and we'll see what else we have in here. So I'm going to go ahead and, in fact, actually, I'll do this part on camera because this is really easy. I'm going to go ahead and just pop off these 2 hex nuts right here around the SMA, and we'll see, whoopsies, there we go. We'll see. Now normally I have to pull this out, but just lifts out like this, and aha, there are all the screws. That looks like RF screwed into me. And again, the model number, this is the part, this is the serial number I said was hidden. So this is the actual HP model number for the OEM the OEM model number, I should say, for the attenuators. This would be the actual part number. So if it was a non-HP OEM, they'd probably have their own part number on here. This is HP's part number for the 8642B specifically. So this is, you know, those funky, crazy part numbers. But anyway, so you can see inside here, this is the actual OEM model number. If you were to buy it from HP to use within your own equipment, this is what you would see. And I haven't found yet a data sheet for the S. You can look up 33321 A through G variants of this, and they have the data sheet online, and you can see they all seem to be relatively of the same family, so they're all sort of similar. They've got some mechanical ones that are have cams here instead of solenoids, but in any case, yeah, so it's easy to look that up. So I'm going to go ahead and pull off all of these, and we'll see what's inside here. One thing to note, so all the screws are out. One thing to note is that, and I noticed this as I was pulling apart, is somebody helpfully, maybe even when it was manufactured, somebody put a marker mark here, so we knew it's possible to easily now know when you pull this module out how it goes back into together to fit properly. So let's uncover the magic here. All right. Oh yeah. Okay, so let's look really quickly at the pad side. So it comes in two sections, obviously, and the mechanical side is on this side, and the pads, the actual attenuator pads, are on this side, along with the two SMA connectors. And let's get a bit of a close up there. We can see that the attenuator pads, I don't know if it comes through on camera very well, but anyway, you can see the attenuator pads are clear. It's almost as if they're on some sort of acrylic or glass. They can come out if you undo these screws. There's two metal flanges that sort of pin it in place. I'm not going to do that because I don't trust myself at all not to break them. But you can see just from the size that this must be the 10 dB pad, this is a 20 dB pad, and this is a 40 dB pad. I've done a quick measurement and visual inspection of these already, so of course there's no cracks, there's no dirt, dust, or anything weird like that. If you measure the contacts to ground, there is it's 50 ohm on both sides for each of these, so everything looks okay from there, the way you would expect it to look. And that looks fine. In fact, there doesn't look to be anything wrong with that, which is unfortunate, because that would be the easy thing to fix. Or I should say to replace. You can find a bunch of these modules on eBay, and you can find just an old mechanical one and just reuse the attenuator pads. Nuts. So, put that aside for a second and start looking at this guy. Now, here is where I believe the problem is. So, it's a little hard to see, but the way this is designed is you have the three different pads, and essentially you've got a part in the middle. So each of these pads are done exactly the same. You've got a part in the middle that does not move. And there are two leaves on each side, so that when the plungers come in like this, you get a leaf, this guy here, contact here, and you get a contact here that come out. So everybody comes across that point in time in their project that goes, what the hell am I doing, and what the hell am I doing wrong? And for me, it was when I decided that I probably wouldn't be able to repair one of these modules, at least not without a set of spares. So I decided, well, I'm just going to go buy another set of attenuator modules on eBay and try whacking them in and see what happens. So I went and picked up a couple of these guys here. Again, it's the same model number, the 33321, in this case SD, but and I said, well, they all have the same attenuator pad, so it's going to work out fine, right, for the same model number. And of course, I just had to make sure I got one that was electrically controlled, so no problem. And there are mechanical versions or mechanically controlled versions of this, and yeah, got the attenuators, whacked them in the 8642B, and they were working perfectly. I tested them really quickly beforehand. The actual mechanical part was working fine. They would click in and out, no problem. All the pads. And of course, I did my final checkout after I put these in, saying, okay, everything's good. Measured the output, and the outputs were wrong, like significantly wrong, and they were going all over the board. I said, wow, what the hell's going on now? Did I break something else? Well, not quite. See, what happened was the insides were the same, right, of those two new attenuators. What was different were the pads. So in this particular model that I bought off eBay, it did not have a 10, 20, and a 40 pad. It had a 5, 30, and a 40 pad. Whoops. Yeah, so of course when I put that in, the output became whatever the hell it wanted to be. The signal generator thought it was dropping in a 10 dB pad and it was actually a 5, or a 20 dB pad and it was actually a 30. So yeah, that was wrong. Pardon me. So what I ended up doing was pulling off the attenuator pad. So this is the attenuator pad of one of the eBay attenuators that I bought, and replacing using the good mechanicals and electrical parts from the eBay attenuators and the original pads that came on the attenuators with my 8642B. I was able to basically create a version or a full attenuator that worked properly. So these are the mechanical electrical parts from the original attenuators and the pads from the eBay attenuators. Now, of course, that happened because I made two mistakes. So obviously the first one was saying, oh, same model number, same everything. Yeah, okay, wrong. And so, of course, I didn't quite get what I expected to get. The second mistake that I made was that inside the 8642B, each attenuator module is different. It's got a different set of pads. So one of them has a set of pads of 5, 30, and 40, right, which is what this guy was. So for a total of 75 dB, but not in 10 dB increments or 5 dB increments even. And the other one was a 10, 20, and a 40 dB. So between the two of them, you had 145 dB of attenuation, controllable in 5 dB steps. And that was where the major issue came, and where everything didn't work out and synchronize properly and looked weird when I was when I was doing the final checkout. So mea culpa. Need to pay a lot more attention to what I'm doing, apparently. Don't trust model numbers. Model numbers can be misleading. And in fact, in the data sheet for these model numbers, it should have been obvious that, in hindsight, of course, that with the same 33321 model, there's actually several variants of it. And it wasn't very well indicated what the variants or what the variant combinations were and how you identified them. But it looks like, and of course, again, in hindsight, the option 75 here actually probably means that it's a 75 dB. And the combinations for, say, 75, 70, 75, and I think 140 was the other one, they're very specific. Like, they'll have certain pads to meet that, or to come up with that full 75 dB attenuation or whatnot. So that's that. Case closed. Signal generator is working now. And now I have a couple of attenuators. So of course this one here needs some work. What ended up happening, what was wrong with this, which was causing this sort of the slow response time when you tried to switch these in and out, was because the O-rings that there are a couple of O-rings here that go on these corners here. Pardon me. And at least on one of these O-rings were completely hardened and just falling apart, crumbling. So I needed to replace those. So I can actually show those to you. Give me a second. Here's one. Oops. Here's an example of what I'm talking about. So you can see, it might be a little bit hard to see, but there's two O-rings here, and there's a plastic plunger. So this plastic plunger would go, these O-rings would go, oops, like, pop this out, they would go in like that. And the tops of these O-rings here, those go into the these parts here. Oops, can you see that? Oh, it's hard to see. Okay, there you go. So these parts right here, so they'll actually just go and slip right in, so they pop through the hole and then slip through, and then they'll lock into place. So that's what actually will push those leaves in and out, and bring the pad in or out of the attenuator path, or the signal path, I should say. So I'm going to repair this guy, obviously. I've got to order some of these O-rings on eBay. They're not super cheap. They're used in watch making or watch repair, so shouldn't be too big a deal. And the other attenuator I do have actually does work. So I now have a spare set of attenuators, so I got to find a project for it. So that will be the next set of videos. Thanks for stopping by. Hope you had some fun and maybe learned something, or at least learn what not to do. And I will catch you next time. Cheers.